two different aspects of logistic regression that we have discussed. One is the hypothesis representation. One is hypothesis representation, and another is decision boundary. How to define decision boundary or classification that we have discussed. Okay. Now in hypothesis representation, we have observed that if there is a curve of S shape, okay, this is 0 and this is 1. And here we get the hypothesis. And this is X, okay? And this is the threshold point value, 0.5. So when this S-shape curve is intersecting this y-axis, so at this point, the intersection point is considered as the threshold, which is 0.5. Okay. Now, when we get hypothesis value is found to be greater than equals to 0.5, then we label y equals to 1. And when hypothesis value is found to be less than 0.5, then we label y equals to 0. Okay. So this is all about hypothesis representation. And then we have talked about decision boundary, how to define a decision boundary for a particular classification problem, binary classification problem. So for that, we have seen a linear hypothesis representation. Then we have seen nonlinear hypothesis representation. And we have defined the decision boundary with the manually defined model parameters. Okay. So in hypothesis representation, what we have seen? So we have seen that we get the hypothesis h theta x, theta 0 plus theta 1 x1, theta 2 x2. Okay. So this is a linear hypothesis representation. Now what we are doing, we fit this hypothesis representation into logistic function. Since logistic regression is used to classify the two classes for binary classification and assign labels for multi-class classification. So we can get this hypothesis representation into this logistic regression function or logistic function or sigmoid function. And for that we get g of z equals to 1 upon 1 plus e to the power minus theta t x. What is theta t x? So theta t x means we will write this theta 0 plus theta 1 x1 and theta 2 x2. Okay. So this is a particular hypothesis representation. We can get many more hypothesis representation for different distribution of data on XY plane. Okay. So we get this entire thing, entire hypothesis representation into this logistic function or sigmoid function. Okay. Which is 1 upon 1 plus e to the power minus theta t x. And after fitting this data, we will see that this function behaves like nonlinear function. Okay. So this g of z is nonlinear function, but the hypothesis representation is found to be linear. Okay. Now we will get this hypothesis representation, and this hypothesis representation, we see that for this particular hypothesis representation, we will get a decision boundary, and with that decision boundary, we can classify two different sets of data, and for that we can assign the class level either 0 or 1 according to the decision according to the distribution of data which are found on either side of uh, decision boundary. Okay, so decision boundary would be linear and non-linear. So we can have decision boundary linear, or we can have decision boundary non-linear. Now, after having the decision boundary, after having hypothesis representation and decision boundary, now we will compute the cost or penalty. Compute the cost or penalty of logistic regression for classification. Now, for that, we can use the linear. We can use the error function for linear regression, and that error function can be used for logistic regression also. And we will see how logistic regression function behaves when the linear regression, when the error function which is used in linear regression is incorporated into logistic regression function. Okay, so here we can write j theta. So here theta is the parameter value. Now, why we need to compute the cost or penalty? Because in the last class we saw that these model parameters theta. So theta, we get theta as column vector, theta 0, theta 1, okay, theta n. So these model parameters we have to determine from the cost function or the penalty function. Okay, and to choose the optimal coefficient or to choose the optimal model parameters value, so we have to first define the cost function for logistic regression. Okay, and then we will minimize this cost function or this penalty function using optimization. So after getting the cost function, we will go for the optimization of the cost function, and then finally we can get the optimal model parameters or optimal coefficient theta for the hypothesis representation. Okay, so that is our objective. So first we made the hypothesis representation, then we made decision, then we define decision boundary. After having decision boundary, now you will define the cost function or penalty function. And after getting the cost function or penalty function, we have to minimize this cost function so that we can get the optimal, coefficient or optimal parameter model parameters, optimal coefficient. Okay, this optimal coefficient is nothing but theta over here. Okay, theta over here. Hello, hello. হ্যাঁ বলুন, বলছি আমি একটু ক্লাসে আছি, আপনি একটু পরে ফোন করবেন, 1 ঘন্টা পরে। Okay, so here the optimal coefficient are nothing but the model parameters and theta over here. Okay, so this is the basic requirements for classification using logistic regression. First of all, we have to we have to make the hypothesis representation, then we have to define the decision boundary, and finally we have to get the cost function or penalty function. And when we get the cost function or penalty function, we will minimize this cost function or penalty function using some optimization technique. And then we will be able to determine the optimal coefficient or optimal parameters. Okay. So now we try to define the cost function for logistic regression using linear regression. Okay, the cost function which is used for linear regression. So j theta is defined as the cost function or penalty function, and we can write j theta equals to 1 upon m summation over half of is theta xi, okay, minus yi square. Okay, so what we are considering here for the cost function. Now here m is 1 to m. This we are getting the summation for m number of what are n number of training examples. So here we can get the training examples x1 y1 x2 y2. Okay, and here we get x m y m. Since this is logistic regression is the supervised learning technique, therefore this class levels y1 to ym all will be associated with the data points x1 to xm. Okay, so here we are having m number of, so we can write xi y xi. So each xi belongs to r to the power m dimensional data. Okay, r to the power m dimensional data. Since there are m number of training examples, and each of uh, and here training examples are associated with the class level y1 to ym. Okay, so x1 y1 to xm ym are the training example, and for n number of training examples we will get the summation over half of h theta xi minus yi. Then we are taking the square of this deviation, so we get the square of this deviation between the actual value and the predicted value, and then we get the summation over this deviation for the trade, and we can define this linear. This is j theta is actually linear cost function. So this is the cost function for linear regression. Okay, now what will happen when we use the cost function which is actually used for linear regression is using in logistic regression. Okay, so what will happen, what are the consequences we will see if we use the cost function which is actually used in linear regression in logistic regression. Okay, now here j theta, we are writing j theta equals to 1 upon m for m number of variables or m number of training examples, I equals to 1 to m. Okay, half of y h theta x I minus yi square. Okay, so this is the cost function for linear regression which we use in logistic regression to define the penalty function, okay, or cost function. Now we can write this part, okay, as cost of h theta x I comma yi equals to half of h theta x I y I square. Okay. Now to generalize this cost function, what we will be doing that we can we can remove this superscript I. Okay, we can remove this superscript I, and we can write cost of h theta x comma y half of h theta x minus y square. Okay. Now what actually we are doing, we get the we get the value of this half of this deviations, okay, half of this square, and then we feed this value into this cost function j theta, okay, and get the summation over for m number of training examples. Okay, now what will happen if we use the cost function, which is actually used in linear regression, to define the cost function or penalty function for logistic regression. Now how the cost function j theta will look like? Okay, let's say so this is our j theta. So how this curve look like? So this curve look like a non-convex curve, non-convex curve. Okay, this is non-convex curve, and in this non-convex curve, we can see there are many local minima. Okay, so we are trying to minimize this cost function, means we need to get the global minima. So somewhere over here the global minima may be found, somewhere over here the global minima may be found, global minima. Okay, so we have to find the global minima somewhere over here, but due to use of the cost function, uh, use of this cost function for linear for logistic regression, so we get this non-convex curve, and in this non-convex curve we can see there are many local minima. Okay, so whenever the journey will start from this point, okay, by guessing by considering an initial guess, let's say x0, okay, then every time when we make a journey, a short journey, then we will start into this local minima. Okay, local minima again, again we make a short journey, then we get a local minima. So in this way we will get the many local minima in this non-convex cost function. So we have to get rid of this problem so that we can get a smooth convex curve like this, and sum over here. So j theta should become this convex curve, this, which will look like this curve. Okay, this is the much more smooth, much more smoother than this non-convex curve. In the non-convex curve, we can see there are many local minima. Okay, and to get rid of this problem of local minima issue, we can use some other cost function which will be defined in different way. Okay, and the cost function that we can define for the logistic regression called cross entropy cross entropy cost cross entropy cost function. Okay, cross entropy cost function. So instead of using this cost function, we can use the another cost function which is known as the cost cross entropy cost function for logistic regression, so that we can get this uh, smooth convex curve for j theta, and over this somewhere at this point we will get global minima. That means if we start from x0, the initial guess, so this is the x0. Okay, this point is the x0, and we will take every time we will take a shorter distance and get the gradient, and the points at which we get the partial derivative for the gradient. Then with this short with this uh, shorter distance we can approach to this global minima. Okay, approach to this global minima, and this function will converge at some point which is called global minima. Okay, so sum over wherever we will get this global minima. Now how the cross entropy cost function will look like. So we will see now how the cross entropy function look like, and we will fit our data into that function, and we will see how the cost function is determined. After having the cost function, then we will go for minimization of that cost function using some optimization technique. Now we will write cost of h theta x comma y. We will write minus log of h theta x. So here h theta x is the hypothesis representation which we get into this logarithmic function minus log of h theta x. Okay, so which can be defined if y is found to be 1. That means the class level is found to be positive 1. Okay, and otherwise we will get minus 1 minus log of h theta x. Okay, h theta x if y is found to be 0. That means if the class level is found to be negative or class level is found to be 0, so you will get the second cost function which is minus 1 minus log of h theta x. So we get this hypothesis representation into this logarithmic function which is minus 1 minus log of h theta x if y is found to be 0, or if the class level is found to be 0 or negative. Otherwise, for the positive class or the class level 1, we will get the logarithmic function which is minus log of h theta x. Okay, so this is the cost function for this two cost functions combinedly known as cross entropy cost function. Okay, now we can observe that when y equals to 0 or y equals to 1, if this is found to be always true for this cost function, so we can get the cost function in the combined form. So we can write the cost of h theta x comma y equals to, we will write minus y into log of h theta x. Okay, minus we can write here we will write 1 minus y, okay, into log of 1 minus h theta x. Okay. So when we combine both these cost function for class level 1 and 0, okay, so we can get this combined form for the cost function cost of h theta x comma y. Now we will see that if y is, if the class level y is found to be 1, then what will happen to this cost function? We will see the cost function becomes, so here we will get the 1, so minus 1, so here we get log of h theta x, okay, and the second terms here we will get 0, because 1 minus 1, so this will give us 0, so 0 into log of 1 minus h theta x, so this will give us 0, so therefore the cost function becomes minus log of h theta x when the class level is found to be 0. Why I am saying this y equals to 0 or y equals to 1 always found to be true for this cost function. So we can prove this when we combine these two cost function for class level 1 and 0, we can see that when the level is found to be 1, then we can get the cost function for the first type, and if the class level is found to be 0, we will get the cost function of the second type when the class level is found to be negative or 0. Okay, so here we can write log of 1 minus h theta x. So here you can see that here we are multiplying when the class level is found to be 1, we multiplying y, then that is the actual value, with the predicted value h theta x. Okay, and this predicted value fits into this logarithmic function, and it is getting multiplied with the actual value y. So when we write this cost function in combined form, so we have to multiply this y with this with the first type of cost function, which is minus log of h theta x, and when we get the class level 0, we have to write 1 minus 1 multiplied by log of 1 minus h theta x. Okay, so both these are found to be true for this cost function h theta x comma y. Okay, now we can get the cost function. So after having the cost of h theta x comma y, we will get this value, or fit this value into the cost function, which is 1 upon m I equals to 1 to m. Here I varies from 1 to m for m number of training examples. Okay, and here we will write the cost function h theta x comma y. So this will be getting over here. Okay, this will be getting over here, and then you will get the summation over this cost function for m number of training examples. Okay, m number of training examples. So this will give us the j theta, and when we plot the curve for j theta, then we will get the smooth curve. Okay, and this will become convex function, convex cost function. Okay, and some over here we will get the global minima, and at this point, at this critical point, sometimes this global minima is called the critical points. Okay, because this convex function is bending towards up. Okay, towards up, bending towards up. So here we get the critical points of the global minima, and at this point we will get our cost function to be minimized. Okay, at this point, at this global minima, we will get our cost function to be minimized. So that is the idea. That is the whole idea, to minimize the cost function and get the optimal coefficient or optimal model parameters, which will be fit into the hypothesis representation, and we get the proper or appropriate decision boundary for two class classification or binary classification. So that is the whole idea that we are talking about. Now, if we consider the first type of cost function, so for class level, positive class level, cost of h theta x y. Let me write the two functions: minus log of h theta x for class level y equals to 1, minus 1 minus log of h theta x if y equals to 0. Okay. Now, if we plot these two functions, then what we will see? What you will see? How, let's say h theta x represent along x-axis. Okay, and here minus log of h theta x represent along y-axis. Okay, this is x-axis, this is y-axis. Now, how this functions will be plotted over here? So if we get y equals to 1, so let's say this is our 1. Okay, this is the 1. At this point, so here we will get a curve like this for minus log of h theta x. Okay, and for plus log of h theta x, how can we get the curve? We get the curve like this. Okay, so we are discarding this part. This is for the positive. So for negative, we will get like this. So we are discarding this part, and we are taking the part, we are taking the curve which is placed in the first quadrant. Okay, and this distance is 1, this is 0, this is 1. Now if y equals to 1 and let's say h theta x equals to 1, then what will be the cost function? If y equals to 1 and h theta x equals to 1, then what will be the cost function? So we get this value h theta x into this logarithmic function minus log of h theta x. Okay. So what we will see? The cost function will give us 0. The cost will be 0. Then when h theta x is found to be 0, then what will be the cost? That means h theta, this h theta tends to 0. Okay. And previously we see that h theta tends to this 1. Okay. Now h theta tends to 0. Or if we get the perfectly 0 over here, then what will be the cost? So cost become infinity. So cost tends to infinity. If we get the h theta x tends to 0, then cost tends to infinity. So how could we interpret this? How could we interpret this when we get the h theta x equals to 1 and h theta x equals to 0? That means for the first case, if we consider this class level y equals to 1 and hypothesis representation getting 1, then we can say that if we consider a two class problem like malignant and benign tumors, then y equals to 1, the class level is 1, class level is found to be 1. So therefore the tumor is found to be malignant tumor. Okay, tumor is found to be malignant tumor. That means that hypothesis representation crosses the threshold value 0.5, and if the hypothesis value is found to be perfectly 1, then we will get the cost function 0, because we get the deviation 0, and for that we get the cost function 0. But when the hypothesis representation is found to be 0 despite having the class level 1, then something is some consequences we will see. What will be the consequences? The cost function becomes, or cost function, cost value of the cost functions will tends to infinity. Okay, so that is not possible. That means in one side we are claiming that the class level is found to be 1. That means the tumor is found to be malignant tumor. On the other hand, we are saying that the cost function is found to be 0, or it is tends to not it is or it is tends to infinity. Okay, the cost is not 0, but the cost is found to be infinity. Okay, so this is quite impossible. But when the class level is found to be 1 and the hypothesis representation is found to be 1, then cost function will be found to be 0. So this is possible, but for the second iteration, so this is not possible when the hypothesis representation is found to be 0 and class level is found to be 1. In that case, the cost function will give us the infinite. Okay, so that means this curve will not the so it will go this curve will go parallel to this y-axis. Okay, so this is called the infinite. The value of the cost is infinite when the hypothesis representation is found to be 0 despite having the class level is found to be 1. Okay, now if we consider the second type of cost function for class level 0. Okay, now for this we will consider the second type of cost function when the class level is found to be 0. So how to get the curve? So here x-axis we represent h theta x, okay, and y-axis what we get? This is our x, this is y, and this is minus 1 minus log of h theta x. Okay, now we will get the cost function like this. Okay, and this is our 1. That means if we see consequences, then we can observe if y equals to 0. Okay, that means if the class level is found to be 0 and h theta x is found to be 1 or tends to 1, then what will happen? The cost function will be found to be 1. Okay, if y equals to 0 means what? Y equals to 0 means the logistic function is found to be less than 0.5. Okay, or if we get less than 0.5. Okay, or it may happen that h theta x is found to be 0. When it is found to be 0, the cost function will be found to be 0. Okay, that means h theta, when the h theta x tends to 0, then we get the cost function 0. Okay, and when the h theta x is found to be 1, here the class level is benign, but we get the hypothesis the predicted value is found to be 1. So what will happen? We will get the cost function is found to be infinite. That means the perpendicular line that we draw on the x-axis at this point. So this is our 1. Okay, this is 1, this is 0. At the origin we get 0, and at this distance we get 1. So we get the perpendicular line over this x-axis at this point, and the curve which will be found will uh, go parallel to this perpendicular line. But it both this perpendicular line and this curve will never meet. Okay, so that is why we will get the cost function infinite. Okay, or we will get the value of the cost function infinity. Okay, when the y is found to be 0 and h theta x is found to be 1. That means when we get the when we claim that tumor is found to be benign, then what we get? We get the predicted value 1. Okay, so this is not possible. This is not possible. That means the deviation is very large, and for that the cost function will be found to be tends to infinity. Okay, so this curve will never intersect this perpendicular line which is drawn over this x-axis at the point 1 comma 0. Okay, okay, that's all for today. If you have any questions, you can ask me. If you have any questions, you can ask me. Otherwise, we will stop now and we will get this class in the next week. So we'll continue this discussion on the next week. And in the next week, we will talk about optimization techniques. Okay, that's all for today.